All right. If the last section was my favorite thing we've done so far, the next two sections are very, very close. So section 4.5 is the Binomial Theorem. Let's go ahead and jump right in because this is kind of a long section, so prepare yourself, but I don't want to waste any more of your time. So expanding a plus b to the nth power. So we know that an expression of this form, a plus b, is called a binomial. So in theory, we know how to raise this to different powers, but we know that it can start to get tedious. Like, just look, if we're raising this to the fifth power, that's a lot to keep track of. And sorry, I can't draw a straight line. It's a lot to keep track of there. It's not hard. Like, it's basic algebra. We know how to do this, but it takes a long time, and the perfect word for it is just tedious. No one likes doing this. Luckily, if we look at this, we see that some patterns start to emerge. Okay? There are n plus 1 terms, so if we're raising to the nth power, there's one more term than the power, the first being a to the nth and the last being b to the nth power. We notice that the exponents of a decrease by 1 from term to term, while the exponents of b are increasing by 1. And then we notice that the sum of the exponents of a and b in each term is n. So notice, again, we'll look at a plus b to the fifth. Notice how the exponents behave. So a is going from fifth power, fourth, third, second, first, and then if we really wanted to, we can go all the way to a to the 0th power. That's just 1, so that's why we don't write it. Meanwhile, the exponents of b are increasing. Again, we can start at 0 if we want and go 1, 2, 3, 4, 5. And in each term, the exponents of a and b add to the power we're raising the binomial to. Okay. So with these observations, we could expand something like a plus b to the 8th power. We'll ignore the coefficients for now, but we know that we'll start with a to the 8th plus, all right, we're going to use question marks instead of exponents, or instead of coefficients. So plus a to the 7th, but now b is starting to increase. And a keeps decreasing while b keeps increasing. Plus a to the 3rd, b to the 5th, a squared, b to the 6th, a to the 1st power, b to the 7th, and then b to the 8th. So again, ignoring the coefficients, this is pretty straightforward. We don't have to go through the work of multiplying the a plus b out 8 times. We just see this pattern that the a exponents are increasing, the b exponents are, or the a exponents are decreasing, the b exponents are increasing. And again, we'll get to the coefficients. We'll get to the coefficients now. So to complete the expansion, we actually do need those coefficients. Otherwise, this is meaningless to us. It's not helpful. Let's try to find a pattern. A plus b to the 0 power is 1. A plus b to the 1st power is a plus 1a. I'm going to write out 1 plus 1b. A plus b squared is 1a squared plus 2ab plus 1b squared. A plus b cubed is 1a cubed. Now, I already worked all of these out, so you don't have to watch me do that, since we all know how to multiply. 3a squared b plus 3ab squared plus 1b cubed. A plus b to the 4th is 1a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus 1b to the 4th. And then finally, a plus b to the 5th, and we already saw that up here, 1a to the 5th plus 5, or not, yes, plus 5a to the 4th b plus 10a cubed b squared plus 10a squared b cubed plus 5b to the 4th, or 5, sorry, again, a lot to keep track of. This is why we're going through this trouble. A b to the 4th plus 1b to the 5th. Okay? is there a pattern? Hopefully most of us have heard of Pascal's triangle. That's exactly what this pattern is. So just look at the coefficients. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. This is called Pascal's triangle. Each entry, except for the ones on the ends, is the sum of the two entries diagonally above it. So this 2 is 1 plus 1. This 3 is 2 plus 1. 4 is 3 plus 1. 6 is 3 plus 3, and so on. It turns out that the coefficients of binomial expansions, just like these, follow the rows of Pascal's triangle. So, how is this helpful? Well, instead of having to multiply this out, we know the rules for the powers, and now we know the rule for the coefficients. So this first row is for the 0th power, first power, second, third, fourth, fifth. So I need the 7th row, 1, 6, 15, 20, 15, 6, 1, 1, 7, 21, 35, 35, 21, 7, 1. That was the 7th row. That means that's the row that I'm looking at. So find the expansion of a plus b to the 7th power using Pascal's triangle. Well, my coefficients are 1, and I start at a to the 7th, and then the powers of a are decreasing, the powers of b are increasing, plus 7 is my next coefficient based on this row. 7, a to the 6th b, plus 21, a to the 5th b squared, plus 35, a to the 4th b cubed, plus 35, b to the, sorry, a lot to keep track of. A cubed b to the 4th, plus 21 a squared b to the 5th, plus 7 a b to the 6th, plus 1 b to the 7th. Okay, that's that expansion. So using my power rules and using my rows of Pascal's triangle, I can expand a plus b to the 7th power. All right, it's kind of a lot, but that's a lot less work than we would otherwise need to do if I was multiplying this binomial by itself 7 times. Going ahead and try example 2. Just be careful and note that here a is 2, but b is negative 3x. So when you're raising all of these to different powers, so to the 5th power means I'm going to start with 1a to the 5th. That's really 1 times 2 to the 5th. And then plus 5a to the 4th b is going to be plus 5 2 to the 4th times negative 3x, and so on. Okay? So just be careful. Know that you're actually plugging in values for a and b. It's not just a and b this time. We'll go through that in class. So Pascal's triangle is nice. It's useful for finding expansions when n is pretty small, like a single-digit number. But I certainly don't want to find the 100th row of Pascal's triangle to raise a binomial to the 100th power. That's a lot, and not something any of us actually have time for. So we need to examine this pattern more closely, and we want a formula that would allow us to directly calculate the coefficients for any binomial expansion. We need some notation first. So I think most of us have seen this before, but the product of the first n natural numbers is denoted by n exclamation point, and it is called the factorial. I really like factorials, so I'm glad we get to talk about it. But again, n factorial here is 1 times 2 times 3 times all the way to times n. And then we define 0 factorial as 1. Okay, so hopefully we've seen that That shouldn't be new for many of us. So now we can look at the formula for the binomial coefficient. So let's read the definition and then we'll break it apart. Let n and r be non-negative integers with r less than or equal to n. So that's a very mathy kind of a definition. N and r non-negative integers, that just means they are either 0 or they're positive, and that r is less than or equal to n. Then the binomial coefficient, denoted by this interesting notation, is defined by this interesting notation equals n factorial over r factorial times n minus r factorial. This interesting notation is read as n choose r. So whatever the top number is, choose whatever the bottom number is. And we're plugging into this formula. And this will give us the binomial coefficient that we need. So let's calculate some of these. And if you want the derivation for this, go ahead and ask me. I won't spend too much time here talking about where this formula comes from, though it is interesting. Calculating binomial coefficients. So part A, n choose, or not n, 9 choose 4 is 9 factorial over 4 factorial times 9 minus 4 factorial. 9 factorial over 4 factorial times 5 factorial. Plug that into a calculator. Your calculator can calculate factorials for you. And this is 126. 100 choose 3 is 100 factorial over 3 factorial times 100 minus 3 factorial. That's 100 factorial over 3 factorial times 97 factorial. I don't need parentheses anymore. Plug that into a calculator, you get 161,700. Big number. Not one I'd want to calculate by hand. And then go ahead and try letter C. I think you might be surprised by the answer. Quite interesting. So let's look at the connection between binomial coefficients and the expansion. So 5 choose 0. You can plug that into the formula. It's 1. 5 choose 1 is 5. 5 choose 2 is 10. 10, 5, 1. If we lay all of our coefficients out like this, it's Pascal's triangle. So the binomial coefficients, like this formula, actually calculates the terms, the entries in Pascal's triangle. That means that we can generalize the expansion of a binomial to what we call the binomial theorem. It looks intimidating, but it's everything we just talked about, just written in very math terms. A plus b to the nth power is my first term of the row in Pascal's triangle times a to the nth, and then my a powers are decreasing, my b powers are increasing, and then I'm just taking my coefficients from that row in the triangle. So use the binomial theorem to expand x plus y to the 4th power. So remember, x is a, y is b. So this is, plug into your formula. N is 4. So 4 choose 0 times x to the 4th plus 4 choose 1, x cubed y plus 4 choose 2, x squared y squared plus 4 choose 3, xy cubed plus 4 choose 4, y to the 4th. My coefficients, go ahead and calculate those, or this is a small enough number where you can just follow the row in Pascal's triangle. Plus 4 x cubed y plus 6 x squared y squared plus 4 x, not x cubed, sorry, xy cubed plus y to the 4th. And that's all there is to it. Yeah, that's how I expand this binomial using the binomial theorem. Going ahead and try example 5. And remember, so n equals 8, a is the square root of x, and b is -1. So be careful when you're plugging in for a and b in your formula. And we'll go through that together later on. All right. What if I just want a single term, though? What if I want a particular term and I don't actually want the entire expansion, or I don't have the time to work out the entire expansion for a power? Well, luckily, we can figure that out. There's another formula. The term that contains a to the r power in the expansion of a plus b to the nth is n choose n minus r times a to the r power times b to the n minus r power. Again, this comes from solid math. If you want to see the derivation, come talk to me. But just know that this formula works in that it is just a formula. All we have to do is use it. So example 6, find the term that contains x to the 5th in the expansion of 2x plus y to the 20th power. All right. So a is 2x, b is y, and n is 20. So the term that contains x to the 5th, well, since there's the 2 in front of it, that's really going to be 2 to the 5th x to the 5th, which is 32 times x to the 5th. So that term is going to be n, which is 20, choose n minus r, which is 5, times 32 x to the 5th, like we just said, times y to the n minus r power. That's 20, choose 15, times 32, x to the 5th, y to the 15th. And 20, choose 15, times 32. Plug all that into calculator, you get, actually I don't want to cover the next problem, 496,128 x to the 5th, y to the 15th. And that's my answer. So in that huge expansion, this is the term that contains x to the 5th. So there are definitely times when we are interested in finding the term that contains a particular power of a number. And this is how we do it. Example 7. This is an interesting example. This is a challenging example, as most of these final examples for these sections have been. So stay with me, and just know that don't worry if this is confusing for you at first. Find the coefficient of x to the 8th in the expansion of x squared plus 1 over x to the 10th power. X squared is a, 1 over x is b, okay? And then n is 10. I want the coefficient of x to the 8th. So you might say, all right, I need x to the 8th. I know that a is x squared. I know that a is x squared. So that's going to be x squared to the 4th, okay? Where r is 4th. But b is 1 over x. So that means I'm dividing out some x's. If r is 4, then that means b is going to be 6, or that means b is going to be raised to the 6th power. So that's actually not going to give me what I want. Which means that I really need to work out my powers on my own. I know it's a little tedious. And then we have x squared to the 8th times 1 over x squared. And I'm looking for the combination that will give me x to the 8th power, because that's what they want. it's none of those. Okay, x squared to the 6th times 1 over x to the 4th. So that's x to the 12th times 1 over x to the 4th, which is x to the 8th. All right, so I found the term that I need. That means I'm raising x squared to the r power, so r has to equal 6. If r equals 6, then my coefficient is from this. N is 10. Choose 10 minus 6, which is 10 choose 4. And 10 choose 4 is 210. So that's the coefficient of x to the 8th in this expansion. And I apologize, I feel like that wasn't particularly clear at all, but that is something that I think needs to be explained more in class. So we will go over this example again in much greater detail together. I just wanted us to see it, so hopefully you can start to wrap your mind around it. All right, so we'll talk about that in class, not to worry. All right, I know this section was long, I apologize, but the binomial theorem is a huge topic in math, and it's one that we really need to know. So that was that. Write down your questions. Go ahead and hit that like button, hit that subscribe button to get tons more interesting math content from your favorite math content creator, Mr. Boothman. Have a great day, and I'll see you in class.